Okay, good morning. Good morning. Thank you get started with the lecture for today. So please turn off your computers, monitors, screens. So as you know already, we have our first exam coming up this Thursday. Yes. But before we get to the review, I have a couple of slides that I need to cover. This is not going to be part of the exam, but it's going to be the last part of the lecture you started last week. So I brought the slides, made copies for you. That's it. Basically, well, before we go to the material, you have the homework with you. I'll ask you to keep it because we're going to discuss it today in class for you to get ready for the exam. But I would like you to submit the homework with the exam on Thursday. So we're going to discuss the homework. You're going to have the opportunity to revise your answers, and then you're going to submit that homework on Thursday. So don't forget to bring your homework on Thursday. What else do we have? So the exam again is on Thursday, and you're going to have an hour and 20 minutes to work on the exam. So we're going to go over the review after we finish with the material for today. So what we have for today is just the Simplex algorithm, but this time I just want you to understand the difference when you're working with a minimization problem. So far we have discussed the Simplex algorithm for the maximization type of problem. Today we're going to discuss the case for the minimization. And also we're going to talk about how can you identify a problem that can have multiple solutions based on the final solution of the Simplex method, and also how can you identify an unbound problem. Okay, so both cases are going to be discussed today. So for the Simplex algorithm, for the minimization case, the Simplex method can be used to solve this type of problem in two different ways. So there's two different methods. The first one, basically what we're going to do is we're going to use the same methodology that we use for the maximization problem, but we're going to modify the problem a little bit. So the optimal solution in the point x1 and x2 can, that makes this objective function, the smallest. Equivalently, this point makes the maximization the minus z times, if you multiply this function times minus 1, this is what you're going to get. And if you solve the same problem using that objective function, then that would be the largest point. Okay? So that means that we can find an optimal solution to the LP by solving the following LP. So let's say we start with this problem. We want to solve this using the Simplex method. So one way that you can do that is by just transforming or changing this objective function, multiplying that objective function times minus 1, and solving the problem. Instead of looking for the minimization problem, you're going to look to maximize that objective function, which is equivalent. Okay, so if you maximize the negative or minus 1 times this objective function, it's the same as minimizing this objective function. So the only thing for this method number 1, the only thing that you're going to do is multiply this objective function times minus 1, and then instead of solving for the minimization problem, you're going to maximize the objective function. Okay? And those two problems are equivalent. Okay? So that's the first method. So let me show you. So in summary, multiply the objective function for the minimization problem by minus 1 and solve the problem as a maximization problem. with the objective function minus z. The optimal solution to the maximization problem will give you the optimal solution for the minimization problem. Again, these two problems are going to be equivalent. Okay. Note that the optimal z value for the minimization problem is going to be equal to the negative value of the optimal z value of the maximization problem. So if you find the objective function for the max of the negative of the objective function, if you multiply that, you will get the solution for the minimization problem. Okay, so the negative of the solution that you find is going to be the solution for the minimization problem. Okay, so let's look at one example. Again, we have this objective function. This is a minimization problem, and the objective function is 2x1 minus 3x2. And we have the constraints. So we want to solve this problem using the simplex method. So in solving this, modify LP, use minus z as the basic variable in row 0. After adding the slack variables x1 and x2, the constraint will obtain the initial tableau. So this is going to be the first tableau, or the first table. So what we are doing is, we get the objective function. So the original objective function was minimization of z, and this was equal to 2x1 minus 3x2. Okay, so that was our original objective function. Now what we're saying is we're going to solve the max of minus z. So you're multiplying this objective function minus 1. Right? And if you remember, in order to solve the problem using the simplex method, you need to modify the objective function into a canonical form, which means that you're going to move the coefficients and the decision variables to the left side. So this is plus 2x1 minus 3x2. Okay, so this is what we're going to put here in our first row. So minus z, coefficient of minus z is 1. The coefficient of x1 is 2. And the coefficient of x2 is minus 3. And the slack variables are 0 for the first row, for the 0 row. Then the first row represents the coefficients for the first constraint, and the second row represents the coefficients for the second constraint. So we have our first table. Now, based on this table, which variable will enter the basic solution? We are solving as a maximization problem, so you need to look at the first row, right? And you're going to find the value that is the most negative. So in that case, will be x2, right? So minus 3 is the most negative value, so x2 will enter the basic solution. And what will be the row that you're going to use to enter that variable? For that, you have to look at the ratio, right? So you take this column and you divide that column by the right-hand side, and you find that 4 divided by 1 is 4, and 6 divided by minus 1, you cannot divide that because it's a negative number. So that's why we have a none here. So the only one that you can use to pivot that variable is the first row, row number 1. Okay? So when you pivot that, remember you need to make this 0 and this one 0, and that's what we did here. Now you have a second tableau, but now you find that none of the coefficients, yes sir?
So when you get a negative number when you're doing that ratio test,
You
don't use that.
No, it has to be a positive ratio.
So below the positive.
Exactly. Okay? So you have a negative ratio, you don't use that, it has to be a positive ratio. Good question. Okay? So when you go to the next step along, you'll see that you don't have any negative coefficients. You have found your optimal solution. The optimal solution is minus 12 with x1 equals 0, and x2, which is in the second row, equals 4. That's your optimal solution. Okay?
Okay. So your pivot is going to be the x2 row 1.
Your pivot is going to be this number.
Okay. So you want zeros above and below.
Exactly.
That's it.
Yes.
Okay.
So you're going to use the row operations, the Gauss-Jordan method, to make this number 0, but you know that you're going to modify the other numbers as well, right? So you found the solution, minus z equals 12, but since this is a minimization problem, we did that first modification, remember? Now, we need to multiply that objective function times minus 1, and the objective function will be minus 1. Okay? And that's it. That's the solution for the minimization problem. Okay? So I'm skipping the details for the row operations. If you have questions about that, I can go in detail. I'm assuming that you already know how to perform those row operations for Tableau. But if you still have questions, just stop by the office or you can talk after the lecture. Okay? So this is the optimal for that problem. The second method is, I think, is more simple. A simple modification of the Simplex algorithm can be used to solve the minimization problem. So you can modify step 3 of the algorithm as follows. So if all known basic variables in row 0 have a non-positive coefficient, the current basic feasible solution is optimal. If any known basic variable has a positive coefficient, choose the variable with the most positive coefficient in row 0 and enter that value. Okay, so instead of looking for the most negative value, you don't do anything with the objective function. You keep the problem, the minimization problem. You keep your objective function. But now instead of looking for the most negative value in your first row or row 0, you look for the most positive value. Okay, and that will be the one that will enter the basic solution. So now, this modification of the Simplex algorithm works because increasing a non-basic variable with a positive coefficient in row 0 will decrease the value of the objective function. Okay, so it's the same way of thinking as the maximization problem, but now instead of looking at the most negative value, we're going to look at the most positive one because we want to decrease the objective function. So let's look at the example. It's the same problem. The only difference now is that we have a different row 0 because we are not multiplying the objective function times minus 1. So we keep the objective function as it is. This is a minimization problem. So when you look at the initial tableau, you'll find that the most positive value in this row 0 is 3. So you will enter the same variable as you did for the first method. Okay? So now you will enter that most positive, so that corresponds to x2. You do the same process for the minimum ratio, and you'll find the minimum ratio will be that first row, right? So you're going to pivot the same row, and when you do that, this is the next tableau. So now you see that all coefficients for x1 and x1 are negative. You don't have any positive in your variables. So that's your optimal solution. Okay? Z is the coefficient for the actual objective function. So that could be positive, but you would not enter that as a variable. Okay? So you have to look at the coefficients for your value.
So why is it BV, why is it x2 equals 4 and x2 equals 10? How far do you go?
Here. Also, you know.
Well, because up there it's, I know that x1 and x2.
Yes, because when you look at the tableau here, initially the variables that have coefficient 1 and 0 on the other rows are these two. So you know that this value corresponds to S1, this one corresponds to S2. So S1 equals 4, S2 equals 6. Now when you come here, you enter this value, this variable, right? So S2 now has a coefficient of 1. So you know that the value of the first row, instead of corresponding to S1, because S1 just is not part of the basic variables anymore. So X2 is the one that has the coefficient 1 and 0 in the other two. So the value of the right hand side corresponds now to X2. So same thing for this guy here. The coefficient for that row is 1, the other two are 0, so that value here corresponds to X2. Okay? Good question. Okay, so in order to know, the right-hand side, in order to know the value or the variable that is representing that value, you have to look at the actual column. Okay? So that column is the one that is going to tell you have 1, 0, 1, 0. That means that the value of the second row corresponds to that value. Okay? So that's the second method. Again, you're going to get the same solution, but you don't have to multiply the solution times -1 anymore because you're solving the problem as a minimization problem. Okay? Okay, so that basically covers the two methods that you can use for solving a minimization problem using the simplex method. We are now going to transition to when you can identify if you have multiple solutions in your or alternate optimal solution for your problem. So for some LPs, more than one extreme point is optimal. If an LP has more than one optimal solution, it has multiple optimal solutions. So you remember the graphical method when we were solving for one of the problems, I think it was the lab. The line for the ISO profit was, if you remember, it was something like this. So when you draw the ISO profit line, it was touching that line. It was not touching only one point, it was touching the whole line. That's when you have multiple solutions. Okay? So we can identify that case in the simplex method by looking at the tableau. So if there's no non-basic variable with a zero coefficient equals 0 of the optimal tableau, the LP has a unique optimal solution. Okay? If there's a non-basic variable with a zero coefficient in row 0 of the optimal tableau, it is possible that the LP may have alternative optimal solutions. Okay, so if there is a non-basic variable with a zero coefficient in row 0, there's a possibility of having alternative optimal solutions. Okay, so when we find our optimal solution in the tableau, if you find a non-basic variable with zero coefficient, that means that you can have multiple or alternative optimal solutions. So let's look at this problem. The maximization problem, two constraints, two variables. We're going to add those slack variables to make these equalities. So we're going to have 4 variables. So when you write the first table, you'll see that you're going to have -2 and -2 on the first row, or the row 0 for the first 2 variables. So there's you can decide either one you want to enter. It's not going to make a difference in the solution. So if you have the same coefficient, same number, you can decide either one. So let's take x1. So before we get to the next tableau, I just want to see this. So here I'm listing the basic variables. So my basic variables are z, s1, and s2. Non-basic variable x1 and x2. Okay? So in this first tableau, you're deciding to enter x1. And when you look at the ratio, 6 divided by 1 is 6, and 13 divided by 2 is 6.5. So the minimum ratio for those two is 6. So you're going to enter x1 in the first row. So now you need to pivot here and make this number 0 and this number 0. So when you move to the next tableau and make those those operations, you'll find that the second tableau is optimal. You don't have any other negative values here on the first row, or the 0 row, sorry. So that makes the tableau optimal. So that means that x1 and x2, x1 equals 6 is the optimal solution, and x2 equals 0 is the optimal solution. But what happened? You have some non-basic variables here, x1 and x2 are your non-basic variables, that has a value of 0. Okay? So when that happens, that means that you can have alternative optimal solution just by looking at the tableau. So you identify your non-basic variables, and you find that one of those is 0 on row 0. That means that you can have alternative solution. So the optimal solution is z equals 12, x1 equals 6, x2 equals 0. Now, an alternative optimal tableau will be this one. Say we decided to enter x2 instead of x1 in our first step, then you will get a different solution in which x1 will be 0 and x2 equals 6. Okay? So this just to illustrate that these things can happen. If you want to identify if you have multiple or alternative solutions using the Simplex method, you can do it by looking at the non-basic variables and the values of those non-basic variables on row 0. Okay? So, and these two tables are optimal, both of them, but it has different values. They have different values for the variables. Any questions? Again, this is not going to be part of the exam, but I'm covering just to complete the lecture for the Simplex method. The last topic is the unbound LP. So for some LPs, there are 6 points in the physical region for which Z assumes arbitrarily large or arbitrarily small values. When this occurs, we say the LP is unbound. And an unbound LP occurs in a max problem if there is a non-basic variable with a negative coefficient in row 0, and no constraint that limits how large we can make this non-basic variable. So specifically, an unbound LP for a max problem occurs when a variable with a negative coefficient in row 0 has a non-positive coefficient in each constraint and the ratio test fails. And you'll see that with the example. So basically what you're going to see is when you try to make a ratio test for that variable, you will not be able to make it because you have all coefficients for those variables are negative. So let's look at this problem. When you look at the first tableau, this is maximization problems. You're going to enter this x2. It's the most negative variable in row 0. So x2 is the one that you're going to enter. Now, again, what are you going to do next? See if you're following. ratio test, correct? So you found the variable that you want to enter. You have to make the ratio test. So you're going to divide these numbers by the right-hand side. And you'll get that the ratio for the first one, 2 divided by 1 is 2. And 1 divided by 1 is 1. So this one is the minimum. So you're going to pivot this 1. And you're going to make these 2 0. So when you move to the first iteration, I think your notes have an error. So check that you have basic variables z, x2, and x2 and x2, because those are your basic variables at this point, and non-basic variables are x1 and x1. Okay, so now again you perform the same step. You find that x1 is the most negative in coefficient in this row 0. So x1 is going to enter your basic variables, and you're going to pivot this row because the minimum ratio test tells you that this is the only options you have, because that's the only positive ratio that you can get. And again, you are dividing 1 divided by 1, so that's 1. 1 divided by minus 2 is a negative number, so that's why you have no ratio for that particular row. Okay, so you pivot that number, and this is the solution you'll get. Well, what happened now? You have a negative number here, okay, and the coefficients for the first row and the second row are also negative. So there's no way that you can enter this variable because all the minimum ratio tests are going to be negative. When that happens is when you say that you have an unbound problem. So there's no specific solution. The problem, if it is a maximization problem, will go to infinite. Because your feasible region, remember, you have an unbound problem, you can have something like this, and this is your feasible region. This area. And if this is a maximization problem and you have a isotropic curve, let's say the isotropic curve is something like this, when you move that isotropic, it will move this way. So there's no way that you can find a point that basically stop the solution because this space is open. So you will go to it. Okay? So that's what we're identifying using the Simplex method. And this is what the tableau is telling you with this. Okay, so we would like to S2 to enter the basics, but there's no row in which x2 has a positive coefficient. Therefore, the LP is unbound. Okay? Any questions? So that basically concludes the topic on the Simplex method. We're going to talk about other modifications to the Simplex method later in this course. But for now, that's the main algorithm. Something that you can start thinking about is what would happen if instead of having inequalities, you have an equality in your problem. So far we have problems that start with constraints that all of the constraints are inequalities, but we haven't discussed any problems in which you start with equalities in your constraint. So if you start with an equality from start, then adding a slack variable is not an option because the constraint is already an equality. So we're going to have to design another method or discuss another method in which we can go and solve the problem using the Simplex method for those cases. Okay, but for now, for the purpose of the exams, we will cover the Simplex method up to the maximization problem. Okay, so Let's now discuss or talk about the review for the exam. And these are notes that I posted on Sunday. Okay, so for the exam, we're going to have 10 true or false questions. All of them are true or false. If they made the exam, you're going to have 10 true or false questions. Those true or false questions are going to come from the lectures. Okay, so I will advise you to read the lecture, try to understand, note, and if you have questions, just let me know. But those true or false questions are coming from the lectures. And I also posted the lectures with all the notes, so I don't know if you had a chance to look at that. If you missed some of the notes, they are available on Track, so you can print them from the web page. Second section are 4 problems. If you look at the type of problems that we have discussed in class, you can basically categorize them, I will say, in 4 areas. So based on that, you can basically think about type of problems that you're going to see in the exam. Okay? So there's 4 problems. You can expect a formulation, you can expect a graphical solution method, you can expect a simplex method type of problem, and so on. Okay? So those are the 2 sections. In terms of the topics that we cover in class, we went through the review of linear algebras. You might see something coming from this review. So matrices and vectors, the Gauss-Jordan method, linear independence and linear dependence, the inverse of a matrix, and determinants. So that was our first lecture. Second lecture, actually. The first lecture was the introduction. So that's what, just to give you an introduction about the course. That will not be part of the exam, so you can start studying from this part. Lecture number 2. Lecture 3, we talk about the graphical solution to LP problems. So what is the linear program? Feasible region, optimal solution, the graphical solution, and special cases from the graphical method. So you can also identify these cases from the graphical solution. If you have alternative or multiple optimal solutions, if the problem is infeasible or unbound. Now, then we transition to formulation of LP problems. So I think this is going to be the hardest part of the exam. I thought that you're having difficulties in the homework, so I would advise you to, I have the homework with me, so I'll pass it up before we end the class. So I would advise you to review those problems that we discussed in class in the homework problems. Okay, that will give you a good preparation for the exam. So guidelines for formulation, and we went through all these examples. And the last thing we did in class up to today was simplex algorithm. So converting an LP to standard form, transition from graphical to algebraic solution, the preview of the simplex algorithm, and the simplex algorithm itself. Okay, so those are the topics. And we went through them in class. We worked on some labs. We also worked on the homework. Preparation for the exam. I'm saying here, read chapter 2 and 3 up to section 3.3. I think that was the one we covered up to there. So that you can do that if you like to. I believe if you go through the notes, the homework, and the labs, that should be good enough preparation for the exam. But you can also look at the textbook. You can bring a handwritten sheet with formulas. So if you want to include the formulas for matrix, inverse, from the first lecture and make all those formulas, you can do that. If you want to list the steps of the simplex method, you can also do that. What I don't want to see is problems solved in the formula sheet. Okay, so I will be collecting those formula sheets. So I don't want to see a solution of a problem or a formulation for a problem. But you can say to formulate you need an objective function, you need Cartesian variables, all that type of things you can also put in the cheat sheet. No calculator, and you have to turn in your formula sheet with your exam. The exam is closed book, and note you are allowed to use the formula sheet. Clearly show your work and all the formulas using your solution, and this will help me in work for partial credit. So even if you're not sure about what you're doing in the problem, keep writing, try to work as much as you can, because I can award you partial credit. If you leave the problem, if the patient white, there's no way that I can help you. Okay, so always work on the problem. Try to manage your time. You're gonna have 80 minutes, so don't spend 45 minutes in a problem, because a problem is just 1/5 of the total grade. So try to balance the time that you put on each problem. Okay. Any questions? Yes, sir.
There's no calculator. You're not going to put IQ back.
No, it's gonna be something that you, yeah. Basically. So I'm not testing you for the math. I'm testing you for basically knowing what you're doing. Okay. So any other questions? Okay. So let's discuss these problems. I think this is a good review also for this part. So you can ask questions. You already work on these problems for the homework. So what will be the first part or the first thing you will do for this problem? You have the problem in this format, so you need to change this to a standard form. So sorry. Okay. So the standard form, you first have to modify your objective function. So this is c minus 2x1 minus 3x2. And also you need to add those slack variables. So you have x1 plus 2x2 plus s1 equals 6. You have 2x1 plus x2 plus s2 equals 8. And you have x1, x2, s1, and s2 greater or equal to 0. Okay, so you have the problem now in the format that you need to start solving it using the simplex method. So in the exam, I will also provide you with the tables that you're going to need. I will provide you with extra tables. So if you see 20 tables, that doesn't mean that you're going to use all of them. So I'm not going to put 20 tables. I think there's like 4 tables, but that doesn't mean that you will use all of them. Okay, so if you finish the problem without using all the tables, that's okay. Okay, if you use all of them, that can also be right. Okay, so let's start with this problem. You have z x1, x2, s1, s2, right hand side, and ratio. And you start with 1 minus 2 minus 3 0 0 0 0 1 2 1 0 6 0 2 1 0 1 8. Okay, does that make sense? Any questions about how to set up the first table? Okay, so you have a heading for each of the variables and for the right hand side and ratio. And you basically make sure that you don't put the first x here, or the coefficient for the x here, because that corresponds to z. That's one of the things that I've seen a lot. So if you miss that, that will change the actual solution of your problem. Okay, so what would be the first variable to enter the basic based on the first tableau? x2, correct? So that's the most negative value from the first row. So this is row 0, row 1, and row 2. So from row 0, you see that x2 has the most negative coefficient. This is a maximization problem. So you know that x2 is going to enter the basic variable. Now, how do you decide which row to use to enter that variable? Correct, you do the ratio. So you're going to look at this column, okay? And you're going to divide that column by the right hand side. So you have, for the first row, you have 6 divided by 2, that's 3. For the second row, you have 8 divided by 1, this is 8. So you're going to use the minimum, which is this row. So you're going to pivot this number. Okay? So you're going to perform those row operations. You're going to make that 2 equals 1, and then the other two coefficients, you're going to make those 0. So to make this coefficient 1, you multiply this row by 1/2. Once you have that, this number will be 1. So you multiply this by 3 and sum that row here. That will make that coefficients in the top row 0. Then you multiply this by -1 and sum this second row. That will make those coefficients 0. So once you do those row operations, this is the second tableau. x1, x2, s1, s2, right hand side, ratio. So after the row operations, you have 1 minus 1/2, 0, 3/2, 0, 9. You have 0, 1/2, 1, 1/2, 0, 3. You have 0, 3/2, 0, minus 1/2, 1 and 5. And that is after you perform the row operations. Again, if you have questions how to perform those, stop by my office. I will discuss them with you. So that's the next tableau. That's the first iteration. So now which variable will enter the basic variables? Correct. x1 is the only negative actually in row 0. So x1 will enter the basic variables. So you enter this. So we need to look at this and this. So we don't do this one, sorry. So when we divide this 3 divided by 0.5, that equals 6. And we have 5 divided by 3/2, that equals 10/3. Which one is the minimum? Row 1 or 2? Row 2, correct. So you're going to pivot this number. You have to make that number 1. Okay, so you're going to multiply this row times 2/3. That will make this one 1. And then perform the operations to make this 0 and this 0. That will be your second iteration. So we'll go from here to z, x1, x2, x1, x2, right hand side, ratio. And this is 1, 0, 0, 0, 0, 1, 0, 1, 0, 4/3, 2/3, minus 1/3, 1/3, minus 1/3, 2/3, 32, 3, 4, 3, 10/3. So what will be the next variable to enter? Is there any negative values here? So that's the optimal solution. Okay? No negative values in the first row of row 0. That means you found your optimal for the maximization problem. So your optimal solution. So this is optimal. Z equals 32/3. X1 equals 10/3. X2 equals 4/3. S1 and S2 equals 0. That's your optimal solution. Remember, you have to look at the coefficients here. These 1, 0, 0 represents x1. So that means that x1 equals 10/3. 10/3. x2 represented by this column in the second row. x2 is going to be equal to 4/3. Any questions? I'm going to be posting this after the class, so it's good to make notes, but just to give you, also to let you know that that will be available. Any questions?
Well, on the test, you left it somewhere in the calculation, the mathematical calculation.
Yeah, I'll be able to tell if you're following the step.
Okay.
And that's the most important part. If you miss a number, no, that's not going to be. I mean, you're going to lose 1 or 2 points, but you're not going to have the whole problem. Okay. Any other questions? Okay, so let's move to the next one. So in this one, we do the same thing. We start by changing this to standard form. x1 plus x2 minus x3. 3x1 plus x2 plus x3 plus x1 equals 60. x1 minus x2 plus 2x3 plus s2 equals 10, and x1 plus x2 minus x3 plus the slack variable equals 20, and we have x1, x2, x3, s1, s2, and s3 greater or equal to 0. So we do the same thing. Let me write those headings: C, x1, x2, x3, s1, s2, 3 right hand side and ratio. So we start with the problem. 1 minus 2, 1 minus 1, 0, 0, 0, 0, 0, 3, 1, 1, 1, 0, 0, 60, 0, 1, minus 1, 2, 0, 1, 0, 10, 0, 1, 1, minus 1, 0, 0, 1, and 20. Okay? So still, yes sir. Is this like fine?
Yeah.
That's a good observation. Yeah, but it's not the same because you're actually modifying also the right hand side of the constraint. So if you basically look only at this side, it could be if your basic variables at the end are x1, x2, and x3, but you're not sure about that either. Yeah. So it will depend. If you have a case that is ideal, maybe, but you have to consider that you're also modifying the right-hand side. But good observation. So this is the initial tableau, okay? So I'll be the first variable to enter the basic variable. Correct, because x1 is the one with the most negative value in the row 0. So this will enter. Now we have to perform the ratio test to find out which one, in which row we're going to enter this variable. So we look at this and this, and we have 60 over 3, so this is 20. We have 10 over 1, this is 10. And we have 20 over 1, so this is 20. So we're going to enter that variable x1 in the second row. Okay, any questions? And the reason is because the ratio tells you that that's the minimum value. Okay, so we perform those row operations for this pivot, and we find z x1, x2, x3, x1, x2, x3, right hand side, ratio. We have 1, 0, minus 1, 3, 0, 2, 0, 20. One minus 3, 0, 30, 0, 1, minus 1, 2, 0, 1, 0, 10, 0, 0, 2, minus 3, 0, minus 1, 1, 10. Okay, so that will be the tableau after you perform the row operations. So the next variable to enter the basic variables is x2 because it's the only variable that has a negative coefficient on row 0. So this x2 will enter the basic. Now we need to find out which variable which row we're going to use. So we look at the ratio again. So we have 30 over 4, that's 15 over 2. Then we have, this is negative, so we cannot use that ratio. And the next one is 5. So the minimum ratio is corresponding to that last row. So we're going to pivot this number and make the other two equal to 0. You perform those operations, you have z, x1, x2, x3, s1, s2, s3, right hand side ratio. So you will have 1, 0, 0, 3 half, 0, 3 half, 1 half, 25, 0, 0, 0, 1, 1, minus 1, minus 2, 10, 0, 1, 0, 1 half, 0, half, 1 half, 15, and 0, 0, 1, 3 half, negative 0, minus 1 half, 1 half, and 5. Is this the optimal solution? This is a negative. Is this optimal? Yes. There's no other negative coefficient in this row 0. Okay, so you always check row 0 to see if you have any other negative coefficient to enter the basic solution. In this case, there's no other negative coefficient on that row 0, so this is optimal. So what will be the value of x3? Correct. What will be the value of x1? Correct. Okay. So let me write those solutions. Optimal z equals 25, s1 equals 10, x1 equals 15, x2 equals 5, s2 and s3 equals 0. And that's your optimal solution. Questions? Anybody know how to get those solutions? Okay?
X3 equals 0.
Yes, S2 and S3.
So X.
S3 is not part of the basic.
Oh.
So if it is not part of the basic variables, it's equal to 2. That variable is equal to 2. The only ones that have values here is x1, x2, and x1.
What about X3?
X3? Oh, x3 is 0. Yeah, correct. Thank you. Any other questions? Okay, so we have one more. So again, we perform the same steps. So we start with changing the objective function to canonical form. So this is minus x1 minus x2. Then we find the standard format for the constraint. So this is for x1 plus x2 plus x1 equals 100. x1 plus x2 plus s2 equals 80. x1 plus s3 equals 40. And we have x1, x2, s1, s2, s3 greater or equal to 0. So again, z, x1, x2, s1, S2, S3, right hand side. Okay, so I have at least one column. So there's an extra column that I need here. So I'm just gonna add a couple of lines here. Okay, so the initial tableau, this is 1, minus 1, minus 1, 0, 0, 0. This is 0, 4, 1, 1, 0, 0, 300, 0, 1, 0, 0, 0, 1, 40. And I skip one of those. Okay. So this is 1, 1, 1, and 0. This is 8. And this is 1, 0, 0, 0, 1, and this is 40. Okay, so I'll be the first variable to enter the tableau or enter the basic solution. Either one, correct. So it's up to you. Both of them have the same value. So I'll start with x2. So x2 is going to enter the basic solution. So I'm going to perform that ratio here. So this is 100, this is 80, and this is not existing. So I'm going to write x2. Okay. So we're going to enter that x2 in row 2. Remember, this is row 0, row 1, row 2. So we're going to pivot this, and by performing those operations, z, x1, x2, x1, x2, 3, right hand side, we have 1, 0, 0, 0, 1, 0, 80, 0, 3, 0, 1, minus 1, 0, 20, 0, 1, 1, 0, 1, 0, 80, 0, 1, 0, 0, 0, 1, and 40. And that's it. We found the optimal solution after one iteration because there's no negative values in the first row. So the optimal solution z equals 80, x1 equals 0, x2 equals 80, s1 equals s2, and this is 0, and s3 equals 40. And that's the last problem of the homework. So please revise your homework, work on those problems, and submit your homework by Thursday. I have your homework here, so let me pass this Travis. The solution is going to be also posted, apparently. James, Christine, Matt. So if you have questions about the homework, again, the solutions are going to be available on tracks. I'll be available this afternoon and tomorrow if you have questions in general. I'm going to post a note, go over the lectures, the homework, the labs, and if you have questions, let me know right now. Any questions? Okay, so I think that the exam is going to give you enough time to work on the problems. So I'll see you on Thursday, or if you need to talk to me, I'll be here. Okay?